coaches on 581, and we're going to talk about building a strong software team. So just a brief sort of rundown of the structure of this. First off, we're gonna record this. The slides are gonna be posted, and all of our training bonus materials are also gonna be posted after the event. For this presentation, we are gonna have some intros. We're gonna talk about training and student engagement. We're gonna talk about project management, sort of mostly with the focus on software, but sort of in general as a team. And we're gonna talk about software architecture, or as I like to call it, architecting for success. Yeah, it should be pretty fun. The goal of this is, I think, for there to be lessons that you can sort of take home to your team, even if you don't even do software, that there will be like actual stuff that you can take home and use to make your software team better in some capacity. Whether you are like totally new to FRC or you're a very mature team, there should be something in here for everyone. But the idea is that this will be something helpful. So without further ado, let's do some intros. So I'm Jonah. I started off doing FRC as a student on 581. After I graduated, I came back as a coach doing software. Right now I work as a software engineer at this company, Sanity, which only a very niche subset of web developers would know. People keep asking me, where do you work? I'm like, Sanity. They're like, what's that? I don't know. I created DogLog. Raise your, I'm not gonna say no. Well, raise your hand if you've heard of DogLog. Raise your hand if you're a member of Team DogLog, folks. I made FRC colors. I made a lot of other software things, and then Saikiran.
I'm Saikiran. I also work at a small hardware company. I am the coach on Team 581, joined in 2022, and I was a coach on 3476 for 9 years before that, and a student on a team in LA for a while. Oh yeah, so Jonah I think gave a kind of a brief introduction of kind of what we want people to get out of this, but we're gonna make that a little bit more clear. All of this is kind of what we do in our experiences here. And just to provide a little bit more context, hopefully a lot of y'all, I think I saw a lot of faces here at our lab crawl. It was a lot of fun. I know our kids got a lot out of it, but we're just down the street in San Jose. We're a Title I school. Our school has no computer science classes, so all our students have basically no computer science knowledge when they enter the team. So everything that they do in software is all learned on our team. At the end of the 2022 season, when a couple of us joined, there was one returning software student and one software mentor. And Jonah was, I think, 19 at the time. 18? Yes. And now, starting 2025 fall, we have 6 returning software students and 3 software mentors. And we have a very high competency of returning students. I think at the software panel, people asked what percentage of your team has something about the amount of code that students write. So I think our students write, I think our most involved student probably writes 25 to 30% of the code, right? So we, the workload is shared pretty well amongst our students now. So our philosophy here is we want to maximize our performance on field, but also make sure that our students get a really enjoyable experience in the program and get a lot out of the program, right? But we are trying to win. We're still part of a competition team. And excellence comes from the top down. We can't expect our students to be excellent unless they are modeled excellence. And they're modeled how to do things, and they see it happen every day. And a part of that is you have to build good habits with consistency. If you want students to do something, but you're not consistent yourself in how you do things and how you communicate with them, they're not going to be consistent. And another thing, right, is we try to minimize bad failure. I think in FRC, people like to talk about failing fast, right? Failing fast is good, but I think people kind of rely on failure as a crutch for not providing students a good learning experience. They kind of throw students at projects that they know they're gonna fail at, and they're like, okay, we expect them to learn from this. But if there's no good learning, if there's no good end result, right? If there's no good lesson at the end of it, they're not going to learn. They're going to learn that, if they try, they're going to fail, and that's a bad lesson. And again, this is all centered on what worked for us. So take what you want, take what you don't want.
And throughout the presentation, if you have any questions, feel free to raise your hand. We'll try and answer them. The dream is that we're going to yap for 35 minutes and have a little bit of Q&A at the end. Shelby's shaking her head.
Kind of like when you say yeah.
Okay. We're going to have we're gonna have a conversation.
You're gonna deliver a presentation.
We're gonna deliver a presentation. Yeah, and after the fact, please, I assume Saikiran believes this, but like, please come up to me and ask me questions. We are so happy to talk about this, and there is a lot of information. We've sort of touched briefly on a bunch of topics, but like, there's so much that we could sort of talk about, and you should totally do that in the networking thing this evening. Oh no. Okay, let's talk about training student engagement. So a pretty sort of common thing you see in FRC software teams is you have like one, maybe two kids who come in and they probably already know how to code, or at least they know they want to code, or they have, you know, some prior knowledge. And that's sort of convenient because like you don't have to do as much work to teach them, but that's not really the point of like FIRST as a program. We don't, you know, it's like we want to support those kids. It's like, you want to do software, hell yeah, like we'll support you. But like we especially want to appeal to kids who like think they can't do software or want to do it but have like no idea where to get started. It's also just like not sustainable to have like one or two people running all the software because, you know, like what if you get sick or something, or like, I don't know, like that's a lot to put on one person, and it's something you don't super see in a lot of other sub-teams. It's like software especially sort of has this problem. And the reason for that is it's really hard to teach software. I think software in FRC is like probably the single sort of hardest like subject to learn, basically because of this super steep learning curve. You have to put in so much work and effort just to do like the bare minimum, and a lot of students can sort of fall off the track, you know, somewhere along that, because it is so hard to get to that point where like, you know, you're doing something that feels fun and rewarding. And so sort of, you know, what you want on your team is to have some kind of pipeline where students can come in without, you know, maybe no experience, maybe some experience, but they can sort of, you know, get trained and start becoming effective contributors to your team in your software.
Yeah, so what we do is we get started off with the software pathway. We do pathways in our team to get, you know, students caught up on different subjects to start contributing, but we do a software pathway. And the way it's structured is we meet twice a week for 8 weeks, around 8 weeks. And we try to make sure it's very consistent. We, you know, meet for specific times. We give them homework. You know, it's a very consistent structure of class. And it's basic Java syntax to the absolute minimum to get a robot moving. We played with this formula a bit, but you know, trying to get them to the robot as fast as possible gets us the highest engagement and the highest retention in software. So we have online homework to reduce friction. We want to make sure that, especially when students are getting started, they don't have to touch like command line. They don't know, like they don't need to know what like a build system is. They don't need to know what Git is, right? So we use CodingBat. Hopefully a lot of y'all have heard of CodingBat, but if not, it's just like a very simple, it looks like it's from like, I mean, it's from like 2005, right? But you know, they can just type in little problems. They get like, you know, very basic feedback. It's really nice for starting problems. And then LeetCode has custom homework support where you can do your example problems and they can run it in an online sandbox environment. So that's really good when you're trying to, you know, get the students started in the basics. And then at the end of training, we expect students to understand and implement control statements, do, you know, some basic variables, how to, you know, instantiate objects, how to make some basic classes, write some full functions, and understand that they can approach any problem with some help. We go through a lot more in this training, but that's, you know, that's what we expect students to be at the end of the training. This is one example slide from our training itself. This is, I think, probably like 3 classes in, or maybe 2 classes in, where we want to make them like make a motor go when they touch a button, right? So they use some if statements, they use some functions, they use, you know, an integer, and call it a day.
So once students have done this pathway, like Saikiran said, you have just the bare minimum of coding knowledge, not even really hardly robot knowledge at that point. Some students might do that software pathway and realize, I don't like this, and then they leave. But for the students who decide they want to stick with software, one of the things that we do on 581 is we have our new member bot. Which if you're at the lab crawl, you probably saw some remnants of new member bot or heard about it from our students. But the idea here is you have a brand new robot that is sort of, as much as we can, from scratch, all done by our rookie members. So for our new software students, what this means is they have sort of had a very, very structured learning experience so far, and this is a little bit more hands-off, where we're not totally like just like throwing them like you're on your own, but this gives them a chance to sort of apply everything they've learned, and it's in sort of their own environment where they're not sort of going to screw things up maybe for the rest of the team or the other robot. Like this is their thing. They're the only ones using it, and so they're able to sort of totally just do sort of what works for them. And that is with some support from returning students and coaches for things that might be hard. So like one thing that we like doing is we give them sort of the basic subsystems, like maybe you can do an intake and like a pivot control loop or something. But then for maybe swerve or something that's harder, we'll have some more hands-on help there. And then one of the coolest things is like making an auto run, where we'll sort of set up the building blocks for them of like how you can compose this auto, but like actually doing that and tuning that at it's usually at the competition just because deadlines. But that's like a super cool experience of like like this is running your code, like this is your thing. Which that's another thing of like Mike mentioned it. There's my Mike Corsetta reference. But like you want to sort of be like a cheerleader for the students and make them feel proud. Like software is this weird intangible thing, and it can be hard to sort of look at that and feel fulfilled. And so it's important to remind them like hey, every time like we score a game piece, like that's because of your like intake pivot code or something, or that's because like the work you spent like tuning the swerve control loop or something. Anyways.
Yeah, I mean, this is a good example of kind of the pipeline and how it works. So we had a student in 2022 for our off-season event on that robot. Throughout the event, added like one piece at a time for every match, and the team would go crazy every time like the intake moved up. And finally, it scored, a 30, grabbed another game piece from the ground and scored it, and everyone in the stands went absolutely nuts. So that was where he kind of started off as a new software member. He's our software lead today, and in 2024 he our audit doesn't look that impressive, but like there are no paths in this. This is like fully dynamic with vision, and like that's what he was able to do, and kind of how he was inspired to do it from this very basic auto where he took some pre-canned commands that we gave him, chained it together. So it's totally good if you're providing your kids building blocks, because eventually they'll try to start understanding what's underneath those building blocks and go deeper.
Question: the new robot exercises, how does it line up with your season? Are we still pre-season?
Yes, sorry. So this is all off-season. Our software pathway starts sometime in the summer or fall for us. So sort of at this stage, once you've done the pathway, you start a new member bot. That's around October-ish.
It's right now, so we're doing design for a new member robot right now, and then we're going to run it at NatCat. So we run through NatCat or comp bot. We have our off-season bot, which is made by new members totally. We copy another team at new member robot, which is kind of designed by mentors and new members, and then completely assigned by assembled by new members.
Which, so this is for the off-season bot. We've talked about these new students, but like we said, when you finish this training, you're at sort of a very basic level of proficiency. But after a few years on the team, you hopefully have learned some more stuff. And a really important sort of thing to understand is like students are going to be at different levels, and it's important that you don't try doing a like one-size-fits-all training approach, because that's either going to push students out because it is too too advanced for them to sort of succeed, or it's not going to sort of push your students to like learn more. They're always going to be sort of capped at that beginner level. So in parallel, while the new member bot software is happening with our rookie students, our returning students are spending time working on off-season bot, which is writing sort of robot code from scratch. In the past, we've sort of done more hands-off compared to like in season, where again, it's a chance to make mistakes and to learn and to try out things that maybe if you're a student who's like never worked on auto, maybe this is the time in the off season where you get to learn how does like making an auto work. We also like to do our independent projects, where again, a big part of what we do is trying to make the students feel like they have ownership over what they do, and you are working on a team, but you can still have times where you can, have an individual project where it's like, that's just you end to end. So, two examples here. This top one was in 2024. One of our students, Hector, worked on, writing a very complicated, at least to me, physics model to sort of model trajectories of shooting a note. And this was like a whole thing. He like learned how to do Python. It was kind of crazy, but like we just sort of sat him down and said, hey, here's a project. Does this seem interesting? And he sort of thought it was fun, and then he just started cooking. And then after a while, came up, and so we like to have students write a whole post about this, which we put on Chief Delphi, and they come up with a whole little write-up and diagrams, and it's all very, very nice. This is one of the posts there from one of our other software students. So this is sort of a great chance of, in the off season when it's sort of lower risk, to step outside of their comfort zone and try learning more things that they haven't had as much time, maybe in season, to work on.
And to add on to that, we also spend a lot of time trying to develop their project management skills, which is what we're going to talk about in the next section. We try to encourage students and have them actually start planning and training and planning like work being done, doing status updates, doing all the stuff that mentors kind of sometimes do, and then that preps them for the next stage. And then the last step here, right, is you got to get feedback from the kids. And this is something that I was actually recently reminded of because I got feedback from a kid about what was not working for him, and it was really brave that he came up, was able to communicate, right? He was a very special kid. He's always great at this kind of stuff, but it reminded me, right, and us that we have to make sure that we check in with our kids regularly, right? Ask them what works for them, what doesn't work for them. For this specific kid, he was working on small project or small bugs here and there, right? We have extensive GitHub issues. He was solving one ticket after another, and he was not being fulfilled by that. And he wanted a bigger project that he can take on, work for a couple of weeks, have a lot of ownership on, and he got a lot of fulfillment out of that. So we're able to change there. Yeah, do you have a question? Oh, never mind. Sorry. Yeah, and then it's a good way to quickly implement and reevaluate. Yeah, that's it.
Yeah, and this process is sort of what works for us, and that's only after we've been sort of continually iterating. You should not walk away from this presentation with the idea oh, I'm going to copy one-to-one what they've done. This is sort of what works for us and our students, and the sort of key thing here is yeah, you have to iterate. You're not going to get this right on the first time, and you should think of this, as a collaboration of you and your students of trying to figure out how can we, train you? How can we make this work for you? Okay, project management. We're going to speed run this. We have 20 minutes. Okay, so why project management? There's, sort of obviously it's oh, well, you have to do project management to make the project happen. But there's a few reasons which Saikiran will get into.
I think the two key points here is coordination and prioritization. There we go. So you want to make sure everyone is aligned on all the tasks, and you have to make the trade-off with resource allocation, right? To balance learning versus getting stuff done. In the off-season, it's sometimes easier to make that trade-off to bias more towards learning. In season, we make it very clear to the kids, and the kids are all on the same page, so we bias towards performance. And then, important work gets done, less important work gets pushed, right? I think we're all familiar with that in all the different work that we probably all do. And coordination, consistency matters, and consistent communication matters. Predictable routines can make students feel more comfortable and engaged. I try to get some literature to support this. There's tons of papers up about this. The way you want to engage more kids, especially kids who are not really reflected in our programs, right? Especially in software, right? I think a lot of teams, you look at a lot of their programs, right? It's a lot of boys who are doing software. If you want to engage more girls or people different communities who haven't done software, you have to be very consistent in how you communicate and make sure that even if they're new and don't feel represented there and they don't see people like them there, they know they can latch on to this one thing. And they can keep on doing that one thing, and they'll be successful. And then overall, that's success builds on itself. Just build good habits. Yes.
What's an example of that one thing?
Of that one thing they can grab on. For example, we had a kid who, for her, she grabbed onto autos. And then she was able to work on autos. We'll talk more about the project management, but work on those autos and always kind of. That was her thing in software she grabbed onto. She's our team captain now, but that was what she grabbed onto when she first started doing software.
So let's talk a little bit about project management systems. The key takeaway is that the system doesn't matter, it's about buy-in and process. If you have a whiteboard on your wall, that's fine, as long as you come in and you write on it and that gets used. If you have a literal Jira board, as long as it gets used, man, whatever gets the job done. For that buy-in, to get things sort of started, to get the momentum built up, you want to have some kind of champion, probably an adult, one of your coaches, who can sort of help build that habit. But once you start doing it, if your system sort of works, it will become second nature and it'll just sort of happen automatically, which is super cool. I would walk into the shop 30 minutes late because I'm bad at planning, I'm good at project management though, and I walk in and I see oh, the kids have sat down, pulled out their laptop, and they're just pulling GitHub tickets, and they're just working on it. It's what? That's crazy. And they just sort of figure that out after, me sort of pestering them and saying hey, even though we could just talk face to face, we will do that, but also let's try tracking this on GitHub. you only want it to be sort of as complex as it needs to be. If it is super, super simple, it's not going to produce a lot of value. And if it's too complex, that creates friction and no one will want to use it. See Jira. So you want to find that sort of sweet spot of the things that make sense for you to track. We'll show some examples of the kind of stuff that we have. And then, sort of, again, where you use this. If it's a whole separate app and it's super annoying, you are not going to want to do that. It's like the classic thing. Software engineers hate doing, product management. They hate updating their tickets. So you got to do sort of everything you can to make it reasonably nice to use that. And then once everything is in motion, you're basically set.
I think we all see it, right? But every barrier that we introduce for students is exponentially hard for them to overcome, and especially for new students. So do everything you can to make it as easy as possible to do that.
So for us on 581, we use GitHub Projects, which is sort of a layer on top of GitHub Issues. This is nothing special. It is just a way to sort of have an issue title and a little bit of description and some history of who's working on it, or whether or not it's finished or not. We started doing this a few years ago and I've really liked it and slowly sort of been iterating on it. Something that we sort of accidentally figured out is using the issue descriptions is big. What you can do, or what I'll do is I'll be at home and I'll come up with a plan of let's work on these 5 things next meeting, and I'll write a whole description in sort of varying levels of detail. But one of them might be we need a fix, we need to flash this limelight because something bad happened, and I'll write here's the link to the docs, here's whatever relevant code, and that is super big, especially if you want to have multiple students doing software. There's only so many coaches, so giving them that sort of cheat sheet of stuff that they can reference is really helpful. And students, in our experience, are able to sit down, look at that, and just work on stuff end to end, and maybe periodically, ask for help. So here, this is one of our software lead, actually, this is an issue he just made, where, again, it used to be just me making these issues, and now it is I barely look at GitHub, and it's mostly the students running the whole show because they've built up that habit, and we have the right, amount of complexity and the right amount of sort of value that tracking this stuff gives us.
But again, you have to model that behavior, make it consistent. It took us, getting it to us, our kids got to this point, probably a year of doing this, right? Whereas a year of Jonah, being the one who controlled all the tickets, made sure they were being made sure testing the kids on doing it. After that, the kids start using it, right? If that's what they know, that's what they know, and they're not going to change what they know necessarily, right? They'll try new things out, but if you build that habit, right, then they'll do it.
So this is an example of what our GitHub Projects board looks like. This is, again, sort of a suggestion. You don't have to do this. This has the kind of stuff we need. It's got, the name of the issue, the status of it, whether or not, it's in progress, done, if it's blocked, whatever. We have a priority. This is just low, medium, high, super basic, because we don't need more complexity. As much as it can be fun and tempting to do that, it's you got to keep it super minimal or else no one will use it. We have assignees. We block out vaguely sort of the start and end dates that we want for it, and that's it. I guess we categorize it. You can see we've got a few groups there, and that helps us we have an owner for each of those milestones, we call them. But this is probably the kind of detail that you want to have in your system.
And it's also quite useful to go back. During events, or not during events, during home practice, right? Where we're practicing with the robot, kids see something break, they can make a ticket, right? Very easy. And then when kids come in the next day, they can just look at the tickets. And if we try to have owners for different subsystems and different big projects, but if there's a kid who's kind of done with their thing, waiting to test, they'll just look at the GitHub, they'll find the next thing to look at, and they just start working on that, right? It kind of gamifies it. They like working, they like doing the thing, right? So it's just lowering all the friction we can to make sure they're able to write all the code they want to, because they want to be writing code. They love doing it.
Cool question.
Are you only project managing the software for these businesses? Are they fixing robots?
Great question. Yeah, no, that system that we showed is just software, but I'm showing our team-wide project management. Shelby demoed this at our workshop. She's the one who is the champion for it. Jonah's the champion for our software project management. Shelby's the champion for our team-wide project management. But this is this is the big thing that we reference at the beginning of every meeting for our team overall itself, right? And it's not that complicated. I just want to show this as this is just a simple Google sheet that's out there that the kids update, they look at, and everyone looks at, and we can see. I think. It has everything on here. I think Mike mentioned it, right? To go back to Mike, right? It has coach availability on there, has leader availability, it has everything you kind of need, and it's very simple for everyone to look at, edit. Kids pull it up at the beginning of every meeting. We're able to divvy up work, all that. So project management does not need to be complicated. It can be as simple as a Google sheet. It can be as simple as a whiteboard. I actually wanted to bring up the kids just also make their own project management things during season. like in the middle of season this year, like they started like, it was like we couldn't read it at first, but it was like their own queue on the whiteboard to figure out who had priority when testing stuff. Like if the kids see what good project management looks like, they'll start like trying to figure out ways to make it better and try to do things that work for them. All right, so, and this is how we kind of begin work in season. So this was kind of inspired off of some questions I heard yesterday. So work begins on day 1 of season. So we have people setting up a repository with basic framework. And obviously you gotta have people participate in the kickoff process. On the right, we have our first commits in 2025, the day after kickoff. Jonah imported our 2025 code. Some kids deleted some stuff. I like how one kid added all the robot states we would ever need. We looked at it. It was actually pretty accurate, which is kind of funny. But we align high-level requirements, automation, and robot details across the team. Software should not be isolated from the rest of the team, right? We have to work together with everyone. Everyone has eyes on this sheets that we're going to kind of show you in a second. But you don't need to do what we do, right? Obviously, whiteboard, sheets, Slack threads, right? You just got to write it down. You just got to make sure everyone is aligned across the team on robot behavior, functionality, just kind of everything that you need there. And once enough details are flushed out, you can start detailed work, right? Like design does not need to know how many wheels are on a shooter, what kind of motor is on your shooter, like what the shooter looks like before you write shooter code, right? It's like pretty generic and you can just write that code and move on to the next high level thing. So we always make slides. This is actually, Jonah and I don't think we've actually looked at these slides until today and then we pulled them up, but this is the slides our kids made for our OP clone that we're making right now. So this is just 4 of I think probably 15 slides. So it has our driver control binds with status on if they're implemented or not. Details on systems, right? So that's gear ratios, what CAN bus it's on, sensors, things like that, how we home them, and then they have slides on automation. So if we have higher level automation, how do we actually implement that? And like it helps, align the driver with the software, with the mechanical team, with electrical, with everyone, which is very helpful for us.
Which there's some highlighted stuff here. The stuff in yellow is like unknowns, where it's like that's sort of a vague idea of what design has said, but maybe we don't know the exact gear ratio, and we'll have to update that in code. But like for now, we can write most of it as Saikiran said. And then the bottom right, the orange and blue is showing whether or not it's automation driven by sensors or driven by the human. And this is like good engineers, you gotta, plan everything out and then start writing the code. Saves you some time.
And when we started doing this, right, the mentors did all of it. Jonah and I did not have eyes on this until today. So the kids see good behavior being modeled or good processes and we'll start doing it. And this is our final section, architecting for success. This is more mad ramblings from us about how software should be written. So a lot of this stuff I know people will not agree with, but this is how we do things. So our architecture philosophy is obviously do what makes sense for your team, and that's the kind of the big thing here, right? I think people on Chief Delphi, people on Discord, people like to talk about the way they do things, and that's the gold standard, right? We're doing that right now. But that's, I think, very common in FRC, especially how it evolves, right? People are talking about the latest and greatest thing, but I think the team that you want to look at is OP. OP has consistently written some of the weirdest software if you talk to them, and they use some of the oldest methods, and they're the best team in the world, right? Top 5 consistently. So you want to think critically about each decision that you make. Will this produce value for the team, or are you chasing the latest and greatest thing? And you want to avoid purity for simplicity. You want to make sure things are simple, make sure your kids understand the code. And the thing that we like to go back to as a team, I think this is an Adam line, but it's schedule drives decisions. So any decision that you make across the team, right, whether it's in your mechanical side, your software, it's all based on your schedule and your team goals. So you want to make sure that you prioritize your student understanding, and you want to make sure that everything that you do is in service of hitting those goals. So you want to make sure features are as simple as they need to be at first, and if you need more complexity, you can add that on, especially in software. It's trivial to edit software, but want to make sure your base level of complexity is just as complex as you need it to be.
And one thing is you want to give the students good tools to debug. It's sort of the same as if you're working on assembling a robot, you want to have good tools to work with. If if you're not doing logging, you're cooked, man. I hate to say it, but in this day and age, you got to be doing logging. Let's talk about DogLog, folks. Raise your hand if you've heard of Advantage Code. Okay, raise your hand if you have tried and failed to implementing AdvantageKit. It's really hard. AdvantageKit is really hard. And a lot of people think that logging is AdvantageKit, and they just immediately think, I gotta do this, and that's not how it is. You don't have to use DogLog. You could, but like we built DogLog because AdvantageKit was like not the right thing for us. It was too complex. We're big nerds, but we're not nerds like that. So, you know, we have an example here of like, yeah, you just write a line and it puts the thing, and then now you have, you know, you can graph this, you can look at it, like, you know, you've seen AdvantageScope and stuff, but like, this is an essential.
Hold on, I don't know if you've seen this. AdvantageScope is different than AdvantageKit. AdvantageScope is dope. It's awesome. It is like world-class visualizations in FRC. It's as good as industry tools out there. In some cases, it's awesome. You should be using that to debug.
That is a good point. Where yeah, like AdvantageKit, AdvantageScope, two separate things. You don't have to do AdvantageKit. There is, you know, it like people think you gotta go either no logging or like 100,000% simulation logging, IO layers, everything. That is not the case. You can do it simple, and you will still get a ton of benefits from that. Let's talk about software architecture a little. This is something that I am very passionate about, and this is the part where I'm gonna get up here and then start yapping and making people mad maybe. So first thing, subsystems aren't motors. A lot of people in software think that like you have one motor, you make one subsystem, and that is not good. That's not a good abstraction. A subsystem can be anything. Like for us, we have a localization subsystem. That's not linked to any hardware. That is just because localization is its own thing. It's where we fuse in all the data from Swerve and from our cameras and whatever, and you know, it gives us nice interface for accessing that. Subsystems are just a way of organizing code based off of what it does, not just because there is one motor or one sensor. And that's one of the things is like, every time you make a decision, like in software, like think like, why am I doing this? Is it just second nature? And it's like, you know, because like, oh, we've always done it like this. Or, you know, is it because this is actually the best way to write this code? One thing is take advantage of the huge ecosystem from WPILib, from other teams, from your own code from last year to try and reuse things and not like reinvent the wheel every year. There is a wealth of information out there, and you can save so much time by taking advantage of that. And it's good, you know, sometimes to build your own things, and we'll hopefully have time to talk about that some more, but take advantage of that. Another thing, sort of building on the first one, organize code by what it does and not how it is written. I shed a tear every time I'm looking at a team's code and I see you have subsystems and you have commands, and it's like, I don't care if there's a folder full of commands, like I want to see the elevator code or whatever. And this is like a really basic thing, but it's like this principle of like, don't like, you know, we're just on autopilot of like, yeah, you put the commands in commands, duh.
So just really quickly, we made a lot of these decisions because it made most sense for our kids. We tried to follow the WFFA patterns very early on. We did not have success with that. The kids not really get it. We moved to doing more of these things. So rather than like purity of it, right? It was the kids do not understand that, they understand this.
And you know, make good abstractions, which is easier said than done. We got a question in the back.
Yeah, so from a process perspective, like you introduced this section as you feel very strongly about this, which is fine, good. As kids become more confident, to what extent do you enforce this almost belief on them versus letting them define their own standards?
That's a great question. I think as the students, as they get more confident, they start, you know, we hopefully have taught them not to just blindly follow, you know, rules from us rather than rules from like some other people. But yeah, so they will start to question that. And we, you know, have totally, I think, iterated on these patterns and stuff based off the inputs from them. Especially, that's what we like to do in the off-season bot. That is pretty hands-off. And that's the chance where it's like, we might write code like this normally, but like, it's the off-season, you can do whatever you want. And that's where they can play around and experiment with new stuff. Sometimes...
If the kids like have a strong belief they want to try something out, especially in software, you let them try it out. It's like very minimal, like low cost, right? Very minimal. If they feel strongly about something, they tell us about it, then like, yeah, might as well, but like we'll work with them, make sure it actually works, make sure it works with all the kids, and then if it does, you know, we go with it. If it doesn't, we roll with it.
Yeah, so make good abstractions. Real briefly, making abstractions is hard. That's kind of the whole hard part about doing software. Don't make abstract classes just for the hell of it. Don't make a class where it's like, yeah, this is my motor interface that wraps the talent effects. It's like, why? That's not doing anything for you. That's causing problems, probably, like, unless you're Eugene, but like we could do a whole presentation on that. He has done a whole presentation on that. But you know, something like a limelight class, where maybe you got 3 cameras for able tags, and like, sure, yeah, that's a good abstraction. Or maybe you have like a base subsystem thing that logs, you know, a few essential things for you and your team. Like, that's good. But like, don't, try and make a generic, like, this is the elevator generic IO, like, whatever system. Like, you're totally gonna have something you need to change, and you're gonna wish that you had not built some crazy abstraction layer and you could just edit the code directly. And then finally, visibility into logic is vital. State machines, which we'll talk about in a second. The example I like is like, pose estimators and standard deviations. I don't entirely know how to tune standard deviations on pose estimators. Is that because I'm stupid? A little bit. But also, like, that's a bunch of like crazy math. Look at 1690. They're very good. They're very good at like, software and robots in general. They don't use like Kalman filters for pose estimators because it is hard to tune. They do not have visibility into like all that crazy math. What they do is they came up with their own system of like a trust factor, which is just a percentage from 0 to 1 of how much they sort of trust the value. And it's like, yeah, that works for them because they know how to tune that. They understand what's going on there. And so that's the time where, if there is something from WPI, like, sure, use that. But if it's something that is so essential that you really need to know how it works, and like, yeah, build it from scratch, fully understand it.
Sorry, but only do that if you fully understand why you need something different. Unless, like, if not, use the WPI lib thing, right? So go ahead and do that. Use the library from the other team. But unless it's not serving you and your team, then, if it's not, then make your own thing. So yeah, this is, we don't really do commands that much. We tried to go real deep into commands in 2023 to follow, all the patterns that were out there. This is one of our score commands in 2023. I just tried to look through our code base a couple of days ago and I forgot about this monstrosity. But I think commands are really good for certain things, but it's not a one-size-fits-all solution that I think we see, what we tried to do, so we see some other teams tried to do. And I know back in the early, in the 2010s, right? People were a lot more state machine based and kind of moved away from that. We've moved back towards state machines and structuring all our code like a state machine. We still use commands to schedule buttons. They're struggle, right? But to schedule buttons and other things, but everything else is state machine based, right? They're very verbose, but it allows you to see exactly what every line does and what every transition looks like. And our students really picked this up quickly over commands. They struggled for like a year and a half on commands, and then we moved to this. And if you look at some of our code, we have like one state machine that's like 1,500 lines long, right? It's a huge state machine. It's like kind of a mess, but the kids all understand it. I don't understand it necessarily, but I haven't worked on it. But they all understand it. They make changes to it all the time. It works for them. Yeah, the other thing about commands that I didn't really talk about here is it's really hard to debug the transitions between commands and trying to figure out what happens and what's wrong. And every once in a while, we kind of think about going back to commands. We have commands in autofail, and we don't know why transitions happen. And we're like, oh yeah, we're glad we're on state machines for the rest of the code. Yes?
Do you have a sense for why commands didn't stick with the kids? Is what you just said the reason?
Well, yeah, so part of it, but like I think another part of it, right, is you have a bunch of kind of, for succinctness, right, they have a lot of, especially the inline commands, they have a lot of like modifying functions, right, that you can chain together to have very powerful functionality. But that hides how transitions actually work, right? And then when you chain commands together, then you have to have a very deep understanding of when this command starts, when it ends, what can cancel it, what can't cancel it, and it just, it's terrible. It's really hard to do when you're trying to build out really large structure, but with state machines, right, they're so verbose, they're so big because you're explicit about every single thing, and the kids can work with that, right? They can reason through, okay, I have to be explicit about this sort of transition, and when they see it not working out, right, they can open up Sim or the robot, and on Advanced Scope, they see the state it's in, and we're like, okay, I went from this state to this state, I can look to this transition, see what's causing that transition, and they can debug that very easily.
So we're going to briefly talk about some of the state machine patterns that we do. We learned this the hard way. Don't nest state machines. Like Saikiran mentioned, we have a state machine that's 1,500 lines or something, and that is the robot logic. All of our individual subsystems, the claw, our pivots, whatever, those are sort of dumb subsystems. They don't do hardly any logic. They get told what to do by the big state machine, and that's it. They just sort of follow that, and that has worked really well for us. And sure, you have a super unsightly giant file, but it works. Yeah, you have managers and subsystems. A manager is sort of something like that controls the little baby subsystems. That's the thing where it's a manager in our code is a subsystem. That's not linked to hardware. That's just a concept that we have. And yeah, this sort of strict life cycle we're short on time, so we can't super go into it. But yeah, this is what works for us. You can come up with your own thing. Yeah.
Version control, we work on main. We do not like working on branches. Oh, sorry, yeah, question in the back.
How are you teaching state machines in your 8-week teaching section?
Yeah, that's great.
We don't. For the very first 8 weeks, we're just doing the bare essentials. Like, you're just learning sort of how to code. And we like using commands sometimes for that very simple stuff. It just scales poorly. So we start introducing state machines. Typically, when they get to the new member bot or after that project, we start easing them into that.
But state machines aren't fundamentally different from their perspective compared to like if statements that you like have one after another. Right? You take that, that's what we teach, and then we're like, hey, here's a different way of doing case statements, and then here's a state machine, and they learn from there. But we don't like teach them finite state machines. We don't go through all of that, right? It's kind of the use case, and then we teach them like how to, do it. And version control, yeah. So we work on main. We don't really like working on branches, other than for very large refactors. And kind of the way we approach this is all the students are working together, working on main. They work on independent features. They test out. Once a feature is ready to test out, and when it's ready to merge, they merge it in, and they tell all the other students, hey, pull right now, rebase. So there's like, every once in a while, a little bit of friction in rebasing, but this allows like features to very quickly enter, main a robot, prevents a lot of other pain down the line. Yes? How do you ensure that main isn't catastrophic?
It's hard, right? And Jonah will talk about that in a second. We have continuous integration, but it does every once in a while. I think like a couple days ago it was, and Jonah had to write an angry message in Slack asking why main was broken because all the CI tests were failing. Yes?
How do you teach Git and GitHub, and when do you?
Great question. We teach Git and GitHub as part of the software pathway. It's not the first thing because that's friction. We want to teach you how to code, but once we start getting into like, you're going to want to edit like multiple files and we want to track these changes, that's when we start introducing Git. We like using GitHub Desktop because CLIs are hard, and that's a pretty simple GUI. They sort of learn iteratively, and we'll straight up practice like, let's make a PR together. But yeah. So automated testing, like Eugene asked, to keep the main branch good, which is a thing you should all strive for, is like that should be a known good sort of working version of your code. One thing that we have started using this past year is automated testing, like same as any tech startup pretty much. We try to sort of do more unit tests rather than integration tests because that is what works for us. We have a lot of complicated math and all this logic stuff, and we try to unit test that. But for something that's like calling multiple subsystems and maybe it starts needing to use motors, like that's where we draw the line and say, this is going to be a lot of work to maintain, probably will become out of date within a week and is not producing value. But for math stuff, like totally perfect. Catches so many issues way before we actually get that on a robot.
And once you train kids to start using unit tests, like even small unit tests, they can iterate real fast and push out functions really quickly, or push out functionality very, very, very quickly once they know they can test out very small parts of their code.
So simulation, super briefly, just like logging, simulation doesn't have to be hard. We do a lot of silly stuff, which I'll talk about in the next slide. But simulation has been sort of great for us as a team. We tried doing it the fancy physics way, that didn't work. We did it the hacky way, which we'll talk about, and that was great. There was a bunch of unintended effects and some, more obvious things. The things that like, you don't need a robot to test. You can, work from home more effectively. Our students don't have to wait for the robot. So it's like you can do, maybe 4 times as much work because each student is working on their own thing. And one really cool side effect was, without us sort of testing the students, they started working on it from home because they were able to. And that was very sort of cool to see, and we get a lot more done because of that.
In our sims, right, we didn't start from like all of this from day one, right? We did not have sim in 2023, 2024, we have some like limited drive-based sim. 2025, we started with limited drive-based sim, and we heard from the kids that they wanted to test more functionality at home, so Jonah put together the next slide.
So yeah, simulation is not the same as log replay, which is what Advantage Kit is. Simulation is not the same as IO layers, and simulation is not the same as like physics models. Simulation is whatever fidelity works for you, which for us is like, I don't care about the motors. I'm not going to get a perfect model. I'm not going to waste my time trying to do that. I just want to see if like the auto does the right sequence or whatever. So you can see some examples here. The way that we simulate motion is we just pretend that it's following a perfect motion profile, and it's like, it works good enough. The arm kind of moves in sim, and like that gets the job done. Or here, where we say, yeah, in auto, in sim, just pretend it takes a second to intake, because it's like, that lets us test the auto. I don't care if like the sensor isn't perfectly emulated in the simulator, like that's not the goal. The goal is, does the auto work, and can I test that from my laptop?
All right, and last thing on vision processing. So I think a lot of teams are trying to use full field localization. I think everyone is. It's very useful in a lot of cases, but I think getting to that 90% is very easy, but that last 10% of performance is very difficult. The old ways are still good. If you can close the loop directly on an object or a tag, you'll get a lot of high fidelity. It's very simple to test, and it provides more tools in your tool belt. And these are two examples of, we have a node-based intake assist, and then for our 2025 Champs robot, we offset the coral in our arm with the limelight. And we run a color pipeline. And it took like a kid 1 hour to implement this and tune it, right? It's very simple when you just can grab like TX or TY from whatever interface you have and just like plug that into something. So yeah, I'd recommend looking into doing this because it's way simpler than you think. All right, and overall, it's time. Our overall recommendations, minimize bad failures for the kids, maximize their learning and their motivation by removing unnecessary obstacles. So that's with process, but that's also with code. If you need to write some code to make their lives easier and get them to do more things, do that. Make sure they're like excited and motivated and happy to show up every day. And maybe you wrote a little bit more than you wanted to this year, but next year they're gonna start doing that and it's gonna keep on growing like that. Be consistent. Students become more comfortable and can contribute more and are more confident with very clear structure, and start small. You don't have to do everything from day one. Build things up that make sense for you and just keep on iterating. And I think that is it for us.
Thank you so much, everyone, for coming. We can do some questions.
We'll be outside if you want to ask questions. I think we're done, right?
It is 1:01 p.m. So yeah, please come up, talk. We went through a lot of stuff really quickly there at the end. Please ask those questions. We would love to answer it. All this stuff is going to get posted at some point. And thank you again for coming.